Hello friends, in the last few lectures I discussed about fundamentals of radiative heat transfer and basic laws of radiation. In today's lecture I will consider radiation from plane surfaces. So, let us consider a plane surface of some finite thickness. Now, radiation falls on this surface, the radiation coming from some outer source. The radiation that falls on this surface has three roles. It can undergo reflection from the surface. The second part can go into the surface or into the material and get absorbed, and there is a third part, the radiation that is not reflected, neither reflected nor absorbed, will be transmitted through the medium. So, there are three components: radiation reflected, absorbed and transmitted. According to the energy absorbed or reflected, we define three parameters for the surface. These parameters are reflectance, absorptance and transmittance, and together with these three parameters the fourth one is also defined, emittance. Now, reflectance, absorptance and transmittance, these three parameters not only depend on the surface property, but also depend on the radiation, the source of radiation from which the radiation is falling. On the other hand, emittance is purely a surface property. So, we define reflectance as the reflected part of incoming radiation divided by total incoming radiation. When we talk about total, we talk about integrated over all wavelengths. As we will see in subsequent slides, this reflectance, absorptance and transmittance may depend on wavelength and direction also, but here we just give a general idea of these properties. So, reflectance is the reflected part of incoming radiation divided by total incoming radiation, and similarly absorptance is defined as the part of incoming radiation that is absorbed within the medium or the surface divided by total incoming radiation, and the transmittance is defined as transmitted part of the incoming radiation divided by total incoming radiation, and these three components have to satisfy conservation of energy, and that is why the sum of reflectance, absorptance and transmittance should be equal to 1. So, these three parameters, reflectance, absorptance and transmittance, are dependent on incoming radiation, and we will see how to calculate these properties. The fourth one is the emittance, that is defined as energy emitted from a surface divided by energy emitted by a black body, okay, at the same temperature. So, this emittance is a function of surface property, surface parameters like temperature. It may also depend on some other conditions of the surface like surface roughness or some impurity, some coating, okay. So, the parameters that basically define or govern these parameters are temperature, direction, wavelength. So, these are the major parameters basically that decide the amount of energy that is reflected, absorbed or transmitted, okay. But there are some other minor factors like surface finish, okay, roughness of the surface and impurities. Like for example, aluminum surface may oxidize over a period of time and its properties like reflectance and absorptance may change, okay, due to oxidation. So, we will see how these things basically are governed. Now, there are some special classes of surfaces like transparent surface, opaque surface and so on. The transparent surface is the one which does not absorb or reflect any radiation. So, whatever radiation falls on this surface will be basically transmitted, okay. So, many dielectric and non-conducting materials basically come under this category. So, they have very poor reflectance and absorptance, the dielectric and non-conducting materials. Then we have opaque surfaces which have zero transmittance, but they have strong reflectance and absorptance. So, many metals come under this category. They have free electrons, and these free electrons basically are responsible for strong reflectance and absorptance. Then we have reflective surfaces, which are purely reflecting surfaces. They have 0 value of absorptance and transmittance. So, many polished surfaces like mirror, they come under this kind of surfaces. They reflect all the radiation that falls on them. And similarly, we can define non-reflecting surfaces which do not reflect surfaces. So, many non-metallic surfaces, rough surfaces will come under this category. And then there is a theoretically defined theoretical concept of black surface that basically absorbs all the radiation. So, for a black surface, the reflected part and transmitted part of radiation will be 0. All the radiation that falls on the black surface will be equal to absorbed part of the radiation. Okay. And for black surface, the emitted and emittance is equal to absorptance as per Kirchhoff's law. Now, this is absorptance is equal to emittance also has some limitations, we will see as we go further. So, so radiation characteristics of real surface, they depend on temperature as well as wavelength. Okay. As I have already told, these are the major factors, temperature and wavelength. Okay. Absorptance may depend on incoming direction, while emittance may depend on outgoing direction. So, when we have a heated metallic plate and we look at this heated metallic plate, what we find is that it appears very bright when it is viewed at an angle. Okay. It is because the metals have very high emittance when seen from an angle. So, emittance basically depends on outgoing direction. If you look at an angle, it will appear very bright. If you look at the metallic plate, heated metallic plate, normal to it, it may not appear that bright. Okay. Similarly, incoming direction also plays an important role. If the sun is overhead, the amount of energy absorbed by a solar collector is going to be more. If the sun is at an angle, then the absorptance will change and the same amount of energy will not be absorbed. When we are standing in front of fire, our body is exposed to different type of radiation as compared to when we are standing in front of the fire. Okay. And similarly, the reflectance and transmittance will depend on the direction of incoming radiation as well as the direction of outgoing radiation. So, direction plays an important role in radiative heat transfer, and we will see as we discuss each of these quantities. So, the first quantity that we discuss is emittance. Okay. So, emittance is purely a surface property, okay, and it is defined as amount of energy emitted from a surface divided by amount of energy emitted by a black surface at same temperature. Okay. So, we define spectral means at a particular wavelength, and directional, that means at a particular in a given direction. So, for example, we have a surface. So, we are talking about amount of energy emitted in a given direction. So, this is basically E lambda prime, directional emittance, okay, and this will basically nothing I lambda cos theta, where theta is the normal angle. Okay. So, amount of energy emitted in a given direction at a given wavelength divided by same amount of energy emitted by a black surface I b lambda. Now, please note that in expression of I b lambda, I have not used the direction S cap, okay, because the intensity of black body is isotropic. That means, intensity I b lambda is not a function of the direction, okay, it is independent of direction, and that is why in the denominator there is no S cap. So, this is the spectral directional emittance, okay, amount of the fraction of amount of energy emitted in a given direction at a given wavelength. Okay. Now, we define there are two more quantities, spectral hemispherical emittance. Now, hemispherical means integrated over the entire solid angle. Okay. So, the symbol sometimes used is this. Okay. So, we write E lambda, okay, that when we write this, sometimes this is used, or we simply call it spectral hemispherical emittance. We mean basically amount of energy emitted at a given wavelength in all the directions, that is 2 pi solid angle. So, how do we find it? So, epsilon lambda T lambda, that is hemispherical emittance. I have not used the prime here, which is basically denoting the direction. So, this is hemispherical. So, we integrate over the solid angle 2 pi both in the numerator and the denominator. So, we write spectral directional intensity multiplied by cos theta, the polar angle, and integrated over the solid angles. Okay. Now, this intensity from this can be substituted from this expression. So, we can write I lambda as equal to epsilon lambda prime times I b lambda. So, from this, let us call this equation 1, and from equation 1 we substitute the expression for I lambda, and what we get is this expression. Now, under certain assumptions we can take either I b lambda out of this integral or this epsilon lambda out of the integral. Okay. So, we will see this in a while, but for this case I b lambda is independent of direction. So, this can be pulled out. Okay. We can take out I b lambda from numerator as well as denominator, and this expression simplifies to 1 upon pi integral over 2 pi directional spectral emittance integrated over solid angle. Okay. So, this is the expression for spectral hemispherical emittance. Now, we also define total hemispherical emittance, that means integrated over all the solid angles and also integrated over all the wavelengths. So, this is defined as amount of energy emitted integrated over all the wavelengths from 0 to infinity divided by the total blackbody emissive power, okay, EB. So, this basically gives you the expression for total hemispherical emittance. Okay. So, these three quantities are of interest, and all these three quantities are basically dependent on temperature and wavelength and direction. Okay. So, they are purely surface properties, okay, as compared to absorptance and reflectance that depend on incoming radiation. These are purely surface properties. Here is an example that basically shows you the emittance. On the left figure is basically the emittance of some non-conductors like wood, aluminum oxide, copper oxide, glass. Okay. And what we observe, so the x axis, or basically this is on a polar chart, the radius here, the direction of radius basically represents the magnitude of emittance, while the theta direction represents the angle of emitted energy. So, 0 means normal to the plane of the surface, and we see that starting from 0 degree, that is normal to the plane, and up to the value of around 70 degrees, non-metals have very good emittance. They emit good amount of energy in the angle 0 to 70 degree, while they emit very small amount of energy at the grazing angles of 70 to 90 degree in this range. So, if the angle is very large, very less amount of energy is emitted. Okay. So, you should not be able to receive much of radiation from a non-conductor, non-metallic surface if you are looking at the surface from an angle greater than 70 degree. In contrast to non-metals, the right picture shows you the emittance of metals. Now, metals have almost very small compared to non-metals, they have very low emittance in the entire direction, starting from 0 degree to 90 degree. The values varies from 0.06 at 0 to 20 degree here to a value of 1.14. So, the values compared to non-metals are very less, but they are even less at the angles 0 to near normal. So, metals have low value of emittance at normal direction, non-metals have high value at normal direction. Non-metals have poor value of emittance at grazing angles 70 to 90 degree, while metals have relatively high emittance in those range. Okay. So, a metal surface will appear very bright when looked at an angle close to 70-80 degree. It will appear very bright because of the emittance which is higher in this range. Okay. Then we define diffuse emitter or a Lambert surface, in which case emittance is same in all direction. That means, epsilon lambda is equal to epsilon lambda prime. That means it is independent of direction, whatever direction it is coming from is equal. Okay, all the direction the emittance is same. Such a emitting surface is called diffuse emitter or Lambert surface. Okay. So, metals have that I have explained. Then we define gray surfaces in which emittance does not depend on wavelength. Okay. So, in this case epsilon is equal to epsilon lambda, all the wavelengths have the same value epsilon. So, when we have such a surface in which emittance does not depend on wavelength, such a surface is called gray surface. The second quantity is absorptance. Now, as I have already told, absorptance, reflectance and transmittance, they are not purely a surface property, they depend on incoming radiation. Now, we define just like emissive power is the outgoing energy from the surface, we define irradiation H. This irradiation H is basically a magnitude of incoming radiation. So, we have incoming intensity, let us say I, and then we multiply by cos theta, this is basically equal to H, the incoming intensity. So, let us say we have a surface and radiation is falling on the surface with intensity I, okay, and the angle made by this is theta. So, H is the amount of energy falling on the surface, that is called irradiation. Okay. So, we define absorptance spectral, directional is represented with a superscript prime, absorptance at a given direction, in a given direction at a given wavelength, the spectral directional absorptance is defined as ratio of energy absorbed by the surface in a given direction in a given wavelength divided by total energy falling on the surface. So, this is the total energy, total irradiation, and this is basically absorbed part. Okay. So, we define spectral directional absorptance in this way. Now, in thermodynamic equilibrium, and that is basically most surfaces qualify, this can be taken as or assumed as a surface property. Spectral directional absorptance can be taken as a surface property. However, total and hemispherical absorptance cannot be taken as a surface property, as we will see, but directional spectral absorptance can be taken as surface property and it qualifies the Kirchhoff's law. So, emittance, the spectral directional emittance is equal to spectral directional absorptance. This is a surface property. Now, we define spectral hemispherical absorptance, just like we define spectral hemispherical emittance, we integrate over all the solid angles. So, amount of energy absorbed by the surface divided by total energy falling on the surface integrated over the entire solid angle of 2 pi. Now, if by chance we can take out this h lambda out of the integral, or we can take out alpha lambda prime out of the integral, the simplified this analysis. Now, this can be taken out of the integral in two conditions. One is diffuse surface. Now, we already know what is diffuse surface, epsilon alpha lambda is equal to alpha lambda prime. Okay. If alpha lambda prime is equal to alpha lambda, we can take it out, okay. Or diffuse irradiation, that means h lambda prime is equal to h lambda, that means irradiation is independent of direction. So, under these two conditions, either of the quantity can be taken out of the integral and the analysis becomes very simple, and alpha lambda is equal to epsilon lambda. So, this is not a surface property, it is a surface property only if the surface is diffuse or the irradiation is diffuse. So, under these two conditions only we can write alpha lambda is equal to epsilon lambda, otherwise we cannot write it. Okay. Similarly, we define total hemispherical absorptance, okay, by integrating over all the wavelengths. So, alpha lambda T lambda irradiation h lambda divided by total irradiation falling on the surface. Now, again with the same argument we have to take out this alpha lambda or h lambda out of the integral. Now, this can be done in two situations: when the surface is gray, that means alpha lambda is equal to alpha, then we can take it out of the integral, or h lambda is equal to h. Okay. Now, this is very restrictive. Okay. To have irradiation independent of wavelength is very difficult to have in practice. So, mostly this expression will be valid only for a gray surface, that means it absorbs radiation independent of wavelength, the same magnitude, the surface is gray, we can take alpha lambda out of the integral, and then in that case alpha will be equal to epsilon, that means total hemispherical absorptance is equal to total hemispherical emittance. Okay. So, the third quantity is reflectance. There are two types of reflectance, as I have already told. One is specular, the radiation coming from one side at an angle theta and it goes into another direction making the same angle, it follows geometric laws of optics. This type of reflectance or reflection is called specular reflectance, okay, where we have a ray coming at an angle and it reflects back at the same angle. This type of reflectance is specular reflection. Then we have another type of reflection we call diffuse reflection, where we have radiation coming from one side, but it is equally reflected in all the directions. Okay. This is diffuse type of reflectance. So, mostly, so there is no real surface that basically satisfies specular or diffuse. Polished surfaces like mirror, they behave very much like specular reflector. Okay. A polished surface is more like a specular than a rough surface. If you have a rough surface, then it will behave like a diffuse surface, it will reflect radiation in all the directions. The reflectance, the property reflectance will depend on incoming radiation, incoming direction as well as outgoing direction. So, amount of energy reflected coming from this direction and going in this direction, okay, is different from coming in this direction and going in this direction. So, incoming direction as well as outgoing direction both are important. To calculate the value of rho, both the directions are important, the incoming direction as well as the outgoing direction. So, this is just a pictorial representation of specular and diffuse reflection. Okay. Specular incidence angle is equal to angle of reflection, while in reflected, whether the direction of incoming radiation is normal or off normal, all the energy will be reflected equally in all the directions. So, that is basically the diffuse reflectance. So, let us do one problem on the concepts learned in this class. Okay. We have a material surface maintained at 600 Kelvin with directional spectral emittance equal to 0.9 cos theta, where theta is the polar angle, for wavelength range less than 1 micron, and the value is 0.2 for wavelength range greater than 1 micrometer. We have to find out total hemispherical emittance of the surface. Okay. This is not a property that depends on irradiation, this is a purely surface property. We also have to find the relevant absorptance for the radiation coming from the sun. Okay. This is going to be a property depending on the sun radiation. Okay. The angle theta is given as 60 degree. So, let us solve this problem. Okay. We will use this expression for, so we have to find out, let us look at the expression that we have derived. So, we will be using this expression for spectral hemispherical emittance and total hemispherical emittance. Okay. So, we will first find out total spectral hemispherical emittance, spectral hemispherical, okay, epsilon lambda is equal to 0 to pi by 2. So, there is no dependence on azimuthal angle. So, we have already taken out the azimuthal part, the only dependence is on polar angle, epsilon lambda prime sin theta cos theta d theta. Okay. We are basically integrating over all the solid angles, okay, and this will be equal to, so we have been given this value 0.9 cos theta. Okay. So, 2 into 0.9, okay, 0 to pi by 2 sin theta cos square theta, okay, d theta. Okay. We have substituted the value 0.9 cos theta for epsilon lambda prime, okay, and this value will basically come out to be, I am just leaving the integration part to you. So, this will be given by 0.6, the value will come out to be 0.6 for lambda value less than 1 micrometer. Okay. So, for wavelength range less than 1 micrometer, the emittance, spectral hemispherical emittance is 0.6. Now, the same value we can find out for wavelength range greater than 1 micrometer. This will be equal to 2 0 to pi by 2 epsilon lambda prime sin theta cos theta d theta is equal to, now this value is 0.2. So, constant. So, this will be 0.4 0 to pi by 2 sin theta cos theta d theta, okay. And this value will be coming to 0.2, okay, for lambda value greater than 1 micrometer. So, this is the spectral hemispherical emittance. Now, we have to find out total hemispherical emittance. So, total hemispherical emittance will be equal to 1 by sigma T to the power 4, where T is the temperature of the surface 600 Kelvin, integrated over all the wavelengths 0 to infinity epsilon lambda E b lambda d lambda, okay. Amount of energy emitted by the surface divided by amount of energy divided by a black surface. So, this will be equal to 1 upon sigma T to the power 4. We have to divide in the wavelength range 0 to 1 and 1 to infinity, 0 to 1, epsilon lambda is 0.6 E b lambda d lambda plus 1 to infinity 0.2 E b lambda d lambda, okay. And this value we can easily solve. This value will come out to be 0.2, okay. By using this black body emission power tables, we can calculate this expression, okay, and this value will come out to be 0.2. So, total hemispherical emittance is equal to 0.2, okay. Now, we have to find out, so this is the first part, we have to find out the relevant absorptance. Now, solar angle, the solar energy is coming at an angle theta, which is equal to 60 degree. So, we have to find out total directional absorptance, we have to find out epsilon prime, okay. So, this epsilon prime will be equal to 1 upon sigma T to the power 4, where T is the sun temperature, okay, integrated over all the wavelengths 0 to infinity, directional emittance epsilon prime, okay, at an angle of 60 degree, and then E b lambda at the sun temperature d lambda, okay. So, this will be equal to 1 by sigma T to the power 4 0 to infinity. Now, epsilon prime integrated over all the wavelengths 60 degree, okay. So, we have to first evaluate this. So, this will be equal to 0 to 1, okay. We have this dependence 0.9 cos theta, okay. So, we will write this like this 0 to 1 epsilon lambda prime E b lambda d lambda plus 1 to infinity epsilon lambda prime E b lambda d lambda. So, this is going to be epsilon prime at 60 degree angle, okay. And then we just multiply by this will be divided by sigma T to the power 4, okay, and then we multiply by E b lambda T sun d lambda, okay. So, so let us see what I have done. So, 1 upon sigma, so we have to find out directional total absorptance alpha prime integrated over all the wavelengths. So, what I have done is I have taken directional emittance at 60 degree angle integrated over all wavelengths multiplied by solar spectrum E b lambda and then integrated over all the wavelengths. So, 1 upon sigma T sun to the power 4 remains the same 0 to infinity. Now, this epsilon prime is basically done on this type of calculation that we have done in the first part. So, epsilon prime is epsilon lambda prime, for lambda less than 1 micron it will be equal to 0.9 cos theta, okay. So, 0.9 cos theta E b lambda at the surface temperature d lambda and divided by sigma t to the power 4. Similarly, plus 1 infinity epsilon lambda prime E b lambda d lambda, okay, and then E b lambda T sun d lambda. Okay. So, when we solve this, basically what we get is equal to alpha prime is equal to, in 60-degree angle, this will be equal to 0.379. Okay. So, this is our total hemispherical emittance, and this is equal to total directional absorptance. Okay. I thank you for giving your kind attention. So, I wind up this lecture with this numerical problem. Thank you.